Hey everyone, and welcome. If you're deep in the world of pharmaceutical biotechnology, especially for your exams, you know that making drugs is all about precision and, just as importantly, efficiency. Today, we're going to break down a super clever technique that really changed the game for manufacturing some of our most vital medicines. We're talking about enzyme immobilization. Let's get right into it.
So here's what we're going to cover. We'll start with a huge problem that drug makers face. Then we'll zoom in on a classic example, penicillin. After that, we'll look at the brilliant solution they came up with, see how it actually works in the real world, and then we'll wrap up by looking at why this method is just such a massive win. Okay, first up, let's talk about a fundamental challenge that keeps pharmaceutical manufacturers on their toes. It's this really tricky balancing act between making a super pure product and not letting the costs spiral out of control.
And that leads to this big question. Is it even possible to make incredibly pure drugs, which you absolutely have to do for safety, while also keeping your production costs down? For a long time, this really felt like trying to have your cake and eat it too. It seemed almost impossible.
Now, the reason this is so tough comes down to these amazing little biological workers called enzymes. They are just fantastic catalysts, right? They speed up the chemical reactions we need to create drug molecules. But here's the snag. Once the reaction's over, you're left with your drug all mixed in with the enzyme. And getting that enzyme out so you have a pure final product, well, that's a really difficult and very expensive process. To really get our heads around this dilemma, let's look at a perfect real-world case study from the world of antibiotics. This is where this exact problem was a major roadblock for a really long time. So the goal for these companies is to create powerful, modern antibiotics like amoxicillin and ampicillin. You've probably heard of them. They're called semi-synthetic because you start with a natural molecule and then you tweak it in the lab. But to even begin to modify it, you first need a very specific chemical starting block. And that starting block is this molecule right here, 6-APA. That's short for 6-amino-penicillinic acid. The best way to think about it is like the basic frame or the chassis of a car. Once you've got that solid chassis, you can build all kinds of different cars on top of it. Well, 6-APA is that essential core you need to build that entire family of modern penicillins. So, how do you get it? Well, you start with a natural product, penicillin G. Then you bring in a very specific enzyme called penicillin acylase. This enzyme works like a tiny pair of molecular scissors. It finds the penicillin G molecule and just snip. It cuts off a specific piece called the side chain. And what you're left with is exactly what you wanted, the pure 6-APA nucleus. And boom, we are right back to the manufacturer's dilemma. That enzyme, penicillin acylase, is super specialized and really expensive to make. So the old way of doing things was to just dump it into the mix, let it do its job, and then try to filter it out afterwards. It was like buying a really expensive, high-tech power tool, using it for one single job, and then just throwing it in the trash. It's just not practical or economical when you're trying to make medicine on a huge scale. So the industry was stuck. They needed a breakthrough, that big aha moment. And they found it in an idea that was, incredibly elegant and changed absolutely everything. And that big idea is enzyme immobilization. The concept is actually pretty simple, but it is totally revolutionary. Instead of having your expensive enzyme floating around freely in the liquid, you physically attach it or immobilize it onto a solid material that won't dissolve, something like tiny little beads. This way, the enzyme is anchored down and it can't get mixed in with your final product. I mean, just look at the difference this makes. It completely flips the script. Before, with the free enzyme, you had low reusability, which meant high costs and a nightmare purification process. But by immobilizing the enzyme, suddenly you get super high reusability, which slashes your costs and makes purification incredibly simple. It's a total game changer. Okay, so what does this actually look like when you're running it at an industrial scale? Let's take a look inside a bioreactor and see this whole process in action. This is where you see just how beautiful the system is. So, you have a big column that's packed with all those tiny beads coated in our enzyme. You start by flowing your raw material, the penicillin G solution, into the column. As it trickles past all those beads, the anchored enzyme does its job, snipping off the side chains and making 6-APA. Then, a pure solution of your product just flows right out the other end. And the best part? The enzyme never leaves. It stays put, ready for the next batch. It's a non-stop, super efficient production line. All right, we've seen how it works, so let's just bottom line this. What are the actual, tangible benefits? What's the real payoff for doing things this way? Oh, the advantages are huge. First, the big one, Production costs go way, way down because you're not constantly buying new enzymes. This also makes continuous manufacturing possible, which is so much more efficient than stopping and starting. Purification becomes a piece of cake because your product is already clean when it comes out. All of this just adds up to an incredibly efficient process. And the whole thing is built on that key idea. You can reuse that same bed of enzymes over and over and over again. You know, this quote just nails it. It perfectly summarizes why this matters in the real world. This isn't just some cool trick you do in a lab. It's the core reason we can produce so many of our most important antibiotics affordably and at scale. It's the direct solution to that purity versus cost problem we started with. And that brings us to one last thing to think about. We've seen how anchoring just one type of enzyme completely changed antibiotic production. So it makes you wonder, right? What other biological workers, other enzymes, or maybe even whole cells could we immobilize to spark the next big revolution in other fields, like making food or even cleaning up the environment? The possibilities are just fascinating to think about. Thanks so much for joining me today.